Okay, so if we look at our very simplest compound, ethene here, we have different bonds that are present. All right, and these bonds we picture differently. We have our sigma bonds, so all of our single bonds here would be sigma bonds. And one of those two in our carbon-carbon double bond, one of them is a sigma bond. All right, the other one is what? A pi bond. All right, and these are very different in terms of the organization of the electron density. So let's look at these sigma bonds first, okay? So this is the same molecule here, but now we're looking specifically at those orbitals. And a sigma bond is kind of exactly what you would expect with a covalent bond. Let's focus on the middle here, the sigma bond between those two carbon atoms. This is our, what are these orbitals here in this carbon atom? What's the hybridization? sp2. So this is this carbon's sp2. Let me make it a different color so it's easier to see. This is this carbon atom's sp2 orbital. This is this carbon atom's sp2 orbital, and they're overlapping to form this sigma bond. And a sigma bond is kind of exactly what you would expect a covalent bond to be, in the sense that that electron density sits directly between those two atoms that are bonded together, right? These two carbon atoms are sharing this pair of electrons. Where do those electrons live? They live directly between those two carbon atoms, right in the middle. That's that pair of electrons being shared. Okay, so these are all of those carbons' sp2 hybridized orbitals. But remember, this carbon atom had 3 p orbitals to begin with. So 2 of them got mixed up to form these hybrid orbitals. It's still got 1 left over. That's here. So now it's got 1 peanut-shaped orbital left over that didn't get hybridized. All right, so each of those carbon atoms have their peanut-shaped orbital. And it's the overlap of those peanut-shaped orbitals that make our pi bonds. And so for pi bonds, that electron density sits not directly between those two bonded atoms, but it sits above and below those bonded atoms. Kind of not what you would expect with a covalent bond. That electron density that's being shared is being shared above that atom and below that atom, above and below the plane of that bond. All right? We talked about this when we talked about alkenes, like in the first semester. That's what makes alkenes so much more reactive than alkanes. That pair of electrons is so much more accessible because it's not tucked away between those two atoms. It's sitting right out there in the open, on top and on bottom. All right? So this is an important mental picture to have in mind when we're picturing our pi bond. We want to imagine those overlapping p orbitals that are sticking out above and below the plane of that bond. All right? So this is going to be important because now we're going to graduate to the topic of dienes, talking about more than one carbon-carbon double bond in a molecule. And the first thing we're going to do is we're going to talk about the classification of these dienes. All right, we can lump all of our dienes into one of 3 categories. All right, and these categories have to do with how those 2 double bonds are spaced in that molecule. So first we have what we call our cumulated double bonds, which is when those double bonds are located right next door to one another. All right, so here's my double bond in my molecule, and that same carbon atom has another double bond on the other side. This would be a cumulated diene. Why did I draw my cumulated diene like this in this straight line here? What else do we draw on the straight line? Triple bonds. And why do we do them in a straight line? Because they're sp hybridized. Let's look at this carbon here. It's only got 1, 2 bonding regions, so it is also sp hybridized, right? So just like our sp hybridized triple bonds in a cumulated diene, this carbon in the middle here is also sp hybridized. So if we're good, we also draw them in that linear model. Okay, the next one, and this is the title of the chapter, so as you can kind of expect, this is going to be the important one. A conjugated diene. This is when those double bonds are one removed. By that I mean we have a double bond, and then we have a space, we have a single bond, and then another double bond after that. All right, so a conjugated diene has this perfect double bond, double bond spacing. Exactly one single bond separating those two double bonds. All right, and then lastly, our isolated dienes. These are when those double bonds are more than one removed. Meaning there's more than one single bond separating those two carbon-carbon double bonds. In this case, there's two, there could be three, there could be four, there could be a million. As long as there's more than one, that would be considered an isolated diene. Okay? So, now we want to look at these here, but imagine our electron density, our pi bonds and our sigma bonds. And really, we're only going to focus on the pi bonds. Those are going to turn out to be the important ones when talking about these different categories here. All right, so first of all, if we look at our cumulated diene, as we said, this carbon in the middle here, in order to have a double bond on both sides, it has to be sp hybridized. The other two, the ones on the other sides here, these can just be our normal old sp2s. But that one in the middle there has two p orbitals that are involved in overlap. One overlapping to form this pi bond, the other one overlapping to form this pi bond. Right? And importantly, if it's got two p orbitals forming pi bonds, they can't be in the same direction. They're going to have to be perpendicular to one another. So if we were to look at our pi bonds here in our cumulated diene here, what we would see is these perpendicular pi bonds. Right? We have these perpendicular. All right, so if I'm just going to label carbons 1, 2, and 3, carbon 1, 2, and 3, paying specific attention to carbon 2 here. Notice that it has one, let me use a different color. Notice that it has one pi bond going up and down, or rather one p orbital going up and down, forming this pi bond over here. But it's got another p orbital going left and right, or rather going into the page and out of the page, forming its second pi bond. Right? So these two pi bonds here are perpendicular to one another. All right, we're going to go to our conjugated dienes now. What would be the hybridization of this atom? sp2. What about this one? sp2. What about this one? sp2. And what about this one? sp2. So if we have this perfect double bond, single bond, double bond spacing, what we have is a line of all these sp2 hybridized orbitals. And remember, each one of them has that peanut-shaped p orbital sticking out above and below the plane. And so what happens is these p orbitals are all going to line themselves up perfectly. All right? So we have this line of sp2 hybridized carbons. Each one has that peanut-shaped p orbital sticking out above and below, and these atoms are going to line themselves up such that all of those p orbitals are now parallel to one another. All right, so in our conjugated dienes, we have these p orbitals parallel to one another. And the chapter is conjugated dienes, right? So these ones are quite special. So what makes these quite special? The image here kind of shows you with this little blurring that they have, going on here. Remember electrons, we think of them as particles, but we also think of them as waves. They can spread themselves out to multiple positions. So rather than having two double bonds that are just isolated from one another, that aren't talking to one another, what happens is the electrons in these pi bonds are going to smear themselves out and be in all positions at the same time. So these two double bonds here, if we have that perfect spacing, these electrons are going to smear themselves out to be in all of these possible positions here, right? These conjugated double bonds can talk to one another. These electrons can move between these parallel p orbitals here, all right? We would call those delocalized electrons, right? They're not stuck in one place. They're able to spread themselves out across multiple positions. And this spreading themselves out business is going to have a lot of impact on the chemistry of these particular molecules. All right? So when you see this perfect double bond, single bond, double bond spacing, in your mind, you're imagining these parallel p orbitals and these electrons that are smearing themselves out between all of those possible positions, delocalizing across all of those p orbitals. And then let's go to our isolated double bonds here, isolated dienes rather. All right, these are both what hybridization? sp2. And these are both what hybridization? sp2. But what do we got in the middle here? An sp3. And this sp3 does not have any peanut-shaped orbital. It basically messes up the communication between those two double bonds. So now we have these two pi bonds, these overlapping p orbitals, but they're no longer able to talk to one another, right? They can't spread themselves out between both positions. This pair of electrons is isolated to this pi bond over here. This pair of electrons is isolated to this pi bond over here. We don't have any more delocalization, any more spreading of themselves out. All right? So the name of the chapter here is our conjugated pi bonds. These electrons in our conjugated pi bonds are going to smear themselves out between these positions here, spread themselves out across all of those peanut-shaped orbitals. All right, so that's the mental picture that I want you to have. I'm going to sort of now go into the cold, ugly truth of the chemistry behind it, what's called like molecular orbital theory behind this whole thing here. But the most important thing, if you're going to sort of like blur your eyes and get deadhead at the next 5 minutes, is to remember that these electrons are going to delocalize across all of those positions in our conjugated pi bonds. Okay, so now we're going to go molecular orbital theory here. Okay, in molecular orbital theory, our atomic orbitals our p orbitals in this case, mix together to form molecular orbitals. So here are our two p orbitals. One of them is on one carbon atom. One of them is on its neighbor. Right here on the left-hand side, they're separated. But now they're going to mix together, and they're going to form these new molecular orbitals. All right? That's what we call our pi bond. All right? So here is our new molecular orbital. Let's be clear here. This is our atomic orbitals, our p orbitals. And this is our molecular orbital. And we would call this our pi bond. All right? So nothing too crazy, except, of course, physics has to be a little bit of a pain in the ass. And there's always these conservation rules where if I have the number of atomic orbitals that I mix together, I have to get that same number of molecular orbitals. All right, So not only do we get this pi bonding orbital when those mix together, we also get what we call an anti-bonding orbital. All right, the pi bond is our bonding orbital. We also get this anti-bonding orbital. But honestly, we don't really care about the anti-bonding orbital because none of the electrons live in the anti-bonding orbital. They all live in our pi bond. That's why pi bonds form. Okay, so that's a normal old alkene. But now let's look at one of our conjugated dienes. Now we don't just have 2 p orbitals in a row, we got 4 p orbitals in a row. All right. So first of all, they're going to mix together again, and they're going to form our 2 pi bonds. All right, so these are our 2 pi bonds, just like we would expect. But again, this conservation rule, if I mix together 4 atomic orbitals, how many molecular orbitals should I get? 4, right? Mix 4 atomic orbitals, 4 molecular orbitals. You always got the same number. So this is just one of them. All right, there's another one that's even lower energy. And that is when all 4 of those orbitals form one bond. This is now our smeared out conjugated pi bond here. All right, so when we have 4 orbitals mixed together, not only do we get our normal old pi bonds that we would expect between those 2 groups of carbons, we also get one special molecular orbital where all of those orbitals together are sharing those electrons. All right, and these are our 2 lower energy bonding orbitals. Of course, because of our conservation rules, we also have to have higher energy anti-bonding orbitals. But again, we don't have to get too bogged down to that because those are not actually occupied. They exist, but we don't really care about them. All right? So all of this is to say, fancy sort of molecular orbital theory speak for the electrons are going to smear themselves out across these positions in our conjugated pi bonds. Okay, cool? That's what we really need to keep in mind. When we have all these p orbitals all in a row here, we're not going to have one set of pi bonds and another one that don't talk to each other. We're instead going to have all of our electrons delocalize across all of those positions. Cool. All right, so now we're going to talk about stability of our dienes. All right, and just like we saw with resonance and delocalization, the ability of those electrons to spread themselves out has this real stabilizing effect of that molecule. So these conjugated pi bonds here are very stable. They're our most stable type of diene. All right, electrons like to be able to spread themselves out across multiple positions. On the flip side, our cumulated dienes, where we have this weird perpendicular one pi bond crammed right up against the other pi bond, perpendicular. This has this destabilizing effect. These are our least stable dienes. All right, and then isolated dienes, they're really no more or less stable than regular old alkenes. These are kind of in the middle here, our average stability. All right, so when we're looking at dienes here and we're trying to rank them from the most to the least stable, the most important thing that we're going to look at is that classification. All right, I'm going to add a few more. We're going to complicate things a little bit, so I'm going to leave some space here. But now we're going to do an example. I want you to rank from least to most stable these molecules here. All right, we're going to call these A, B, and C. And again, we want from least to most stable. All right, so how am I going to do this? I'm going to go through and I'm going to look at my classification. So what would the classification of A be? Accumulated, conjugated, isolated. A is isolated. What about B? Conjugated. And what about C? Accumulated. And let me just warn you, this is how your homework does it. It looks like one giant long double bond here. There's like the faintest little break. But anyways, if you see that abnormally long double bond, that means that you have a accumulated diene. So then what would be the least stable? Accumulated followed by isolated followed by conjugated. Okay, great. So again, most important factor is going to be our classification of our dienes. All right, but now I'm going to throw another one in there. Oops. We're going to call this one D. All right. Again, step one, classification. What is the classification of this new one? It is another conjugated diene. So then how am I supposed to compare B and D? Based on where they are? Okay, great. So remember, we talked about this all the way back last semester when we were just talking about regular alkenes. The position of these double bonds, and specifically what we're looking for, is what we call, does anybody remember? Substitution. Awesome. Our degree of substitution. By that we mean how many carbons are bonded to those sp2 hybridized carbons that make up our carbon-carbon double bond. So our mono-substituted alkenes, when we just have one carbon neighbor to those sp2 hybridized carbons, those are our least stable. If we look at our sp2 hybridized carbons and we count 2 carbon neighbors, those are our di-substituted alkenes. Those are a little bit more stable. We look at our sp2 hybridized carbons and we count 1, 2, 3 carbon neighbors. Those are tri-substituted. And then lastly, our most stable alkenes are going to be when all 4 possible neighbors are carbon atoms here. Right? So we have this degree of substitution. So if we go back up here and we're talking about diene stability, the first thing we're going to look at is classification. The second thing we're going to look at is degree of substitution. All right, so given that, everybody take a second and throw D in our ranking here. All right, so what we're going to do is we're going to go through, and I'm going to look at this double bond on the left. What would I classify that as, degree of substitution-wise? Mono, di, tri, tetra. Di, right? I'm going to look here at these 2 sp2 hybridized carbon. I got one neighbor over here, one neighbor over here, so this one's di-substituted. If I jump to my other double bond, look at those sp2 hybridized carbons. What would this one be? Mono, di, tri, tetra. Mono. If I play the same game down here, what's my degree of substitution of the bond on the left? This one is di-substituted. And what about the degree of substitution of the one on the right? This one's also di-substituted. So then which one would be my more stable diene here, B or D? D. The more substituted is more stable. All right, and then lastly, we're going to throw one more in the mix here. Call this guy E. All right, I need to do my classification for E. What's that going to be? This one's still conjugated. I still got that network of sp2, 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 sp2. Okay, if I go in and do my degree of substitution, this one's di-substituted. This one's mono-substituted. So it's definitely less stable than D, but it's tied with B in terms of classification and degree of substitution. So then what's the difference? Stereochemistry. And that is our third factor here when ranking diene stability, stereochem. Okay, and so as a reminder here, when we're talking about alkene stereochemistry, let's just take a simple alkene, 2-butene. Well, remember, alkenes cannot rotate about their carbon-carbon double bond. That's not allowed. So this molecule here is distinct from this molecule here. Both of them are 2-butene, but they have different stereochemistry, right? Different spatial arrangement of those methyl groups. We use this EZ stereochemistry. Which one is this one here? E or Z? Z, and how do we know? They are on Z same side. See, it's stuck in your brain because it's the dumbest fucking thing you've ever heard. It's great. Okay, so this is our Z stereochemistry because these two methyl groups are on Z same side. And this is our E stereochemistry. So then which one of these is more stable? E is the one that's more stable. And why is it more stable? Larger groups want to be far apart, right? That's our general principle when we're talking about alkene stability. All right, large groups, in this case, are methyl groups, like to be as far apart as possible, meaning on opposite sides of those double bond, of that double bond. So the last thing here, sort of all else being created equal, we're going to have to look at stereochemistry. And so which one would be considered more, oh, that gave it away. Which one would be considered more stable, B or E? B is more stable, so E is going to sit in the middle here of our ranking. Okay, so this list here is in order of importance. The first thing we're going to look at is classification. That's our coarsest level of being able to separate these out in terms of stability. Then, if they're tied in terms of classification, we'll look at degree of substitution. And if they're tied at both of those, then we'll go to stereochemistry. All right, but this is how we're going to determine our diene stability. Cool. Okay. Next thing we're going to do, any questions before we move on? Cool. All right, so now we're going to introduce our first reaction for this semester here. And this is what's called a Diels-Alder reaction. All right. Before we actually look at the reaction here, we're going to talk about, we're now like exclusively for the rest of the chapter focused on conjugated dienes, right? Those are the interesting ones here. So conjugated dienes are going to be what are involved in our Diels-Alder reactions. We need to first talk about our conjugated diene rotational states, rotational conformations. Okay, and we're going to take a look at 1,3-butadiene here. All right, we got 4 carbons, one double bond located between carbons 1 and 2, the other one 3 and 4. All right, so this would be 1,3-butadiene. And as we just mentioned, we can't rotate about our carbon-carbon double bonds. Those are locked in place. But we can, of course, rotate about single bonds. And so what we're going to do, this is one rotational state of 1,3-butadiene. But now we're going to take this and we're going to rotate about that C2-C3 single bond. Such that our carbon-carbon double bonds are now pointed in the same direction. These are these two different rotational states of 1,3-butadiene. They both have these conjugated pi bonds, right? My p orbitals are allowed to be parallel to one another in both of these cases here. All right, but these are different rotational states. The one on the left, when these double bonds are pointed on opposite sides, we call this the S-trans conformation. And when they're pointed on the same side, we call this the S-cis conformation. Okay. Which one do we think is the more stable of the two rotational states? S-cis or S-trans? S-trans, why? On opposite sides, right? So absolutely, this one is indeed the more stable of the two. Okay, and by that I mean that this molecule spends most of its time in this S-trans conformation, but every once in a while it flips over into this S-cis conformation, and it turns out that this one's going to be the more interesting one for our Diels-Alder reaction. These S-cis conformations are the ones that are Diels-Alder reactive. All right, so when we look at these Diels-Alder reactions, at least to start out with, we're going to be looking at conjugated dienes, but they're going to be kinked into this weird S-cis conformation. And that's because that's the rotational state that will actually react in these types of reactions. All right, so let's take a look at one of these reactions. All right, so a Diels-Alder reaction. A Diels-Alder reaction, and I'm going to sort of put it in a specific orientation that will make sense once we start doing our reaction here. I'm going to kind of lay this molecule on its side. Oops. A Diels-Alder reaction takes place between a conjugated diene, specifically in that S-cis conformation, and the other reactant is what we call a dienophile. Which is super descriptive, because what would a dienophile be? Something that loves dienes, all right? And we'll talk a little bit more next class period about what makes a really good dienophile. For right now, we're going to just note that it has to have a pi bond. Okay, now these deals, I spent a whole lot of time last class period making a big stink about nucleophiles and electrophiles and how we see so many polar reactions in this course. This is like our one example of a reaction that is not a polar reaction. There's no nucleophile and electrophile like we're traditionally used to seeing. Instead, this is what's called a pericyclic reaction. All right, in our reaction mechanism here, we're going to see our electrons move in a circle. All right, remember all of these carbons have these p orbitals here. Our electrons are delocalizing across these p orbitals. Well, in our mechanism here, we're going to see this pair of electrons is going to jump over to this carbon. This pair of electrons jump over to this carbon. And this pair of electrons jump over to this carbon. So we have this circular movement of these pi electrons. All right, so let's look at this arrow carefully. What type of arrow would that be? Breaking and formation. So we're going to break this new carbon-carbon double bond, but we're going to form a new carbon-carbon bond over here. Likewise, same thing over here. So what we're going to get at the end of our Diels-Alder reaction is a cyclic structure, specifically a six-membered ring. All right, and this is like the most important thing to keep in mind about these Diels-Alder reactions. You will always get a six-membered ring product. Why is it always a six-membered ring? Well, the math here, let's look. Our conjugated diene necessarily has these four carbons that are all conjugated with one another. So those are those four. And our dienophile has these two sp2 hybridized carbons that are involved in our reaction. So boom, that's why we get a six-membered ring. Four carbons from our diene, two carbons for our dienophile. That's why we get our six-membered ring. All right. Now, I'm not quite done here with my product. I haven't correctly kept account of all of my electrons. To be clear, this one right here, reaching from this bond to this orange carbon here, that forms my new sigma bond, right, over here. I have a new sigma bond. That's what this arrow did. Likewise, down here, another bond between a green and an orange carbon. I have a new sigma bond. Same thing right here. So those arrows have been accounted for. All right, but this is another bond-breaking, bond formation arrow that's going to move this pi bond from being between these two carbons, let's call them carbons 1 and 2, to now being between carbons 2 and 3. Right? So I now have, to finish off my product here, I have this new pi bond. Or rather, let's call it a move our pi bond. All right, and what we're going to, so we basically grabbed the simplest possible diene. The simplest possible diene, only 4 carbons. You can't have anything smaller than that and still be a diene, right? And we grabbed our simplest possible dienophile, only 2 carbons. And so our simplest Diels-Alder reaction would always creates a 6-membered ring. We just get this cyclohexene product. But this is always going to be the case. Now we're going to start decorating this diene here with a bunch of other carbon atoms, or our dienophile with a bunch of other carbon atoms. Same principle is going to form, right? We're always going to form this same 6-membered ring. Okay, so let's complicate things a little bit and see if we can follow along here. I'm going to keep my same orientation here just to kind of make it a little bit simpler. We'll sort of graduate to rotating these. But here's my diene. Now I'm going to decorate it with a bunch of other carbons. All right, and let's just keep that same dienophile for right now. And I want everybody to take a second and predict the product of this reaction. All right, so what I'm going to do is I'm going to start with what I know is true of all Diels-Alder reactions, which is my product is what? A six-membered ring. So let's just go ahead. I know I can't go wrong starting here because I know that every Diels-Alder reaction is going to form a six-membered ring. Boom. But now I want to figure out where the carbons over here are over here. All right? So what's always going to be true is the carbons that are involved in this reaction are our conjugated diene carbons, these four here, and our dienophile carbons, the two about our carbon-carbon pi bond. Those are the six that are going to make up my six-membered ring. All right, so my six-membered ring, four of them are going to be from those conjugated dienes, the other from those conjugated pi bonds, the other two from my dienophile. All right. So now I got more carbons to account for, right? I haven't accounted for everything that's on the left-hand side. So what we can do that's going to make our lives a little bit easier is let's just go through and number these carbons here. We're not numbering as if we were naming this molecule. We're just numbering to help us keep track of what's what. So I'm going to call these green carbons 1, 2, 3, and 4. And purple carbons 1 and 2. All right, so where am I going with this? What am I going to need to include here? We can do the same thing on this side. 1, 2, 3, and 4. 1 and 2. So what's missing from the right-hand side that's on the left-hand side? Substitutes. Specifically what? What do I need to add? I need an ethyl group on carbon 2. So let's put an ethyl group on carbon 2. What else do I need? Methyl group on carbon 3. Boom. So now I have all of my carbons accounted for. Same number of carbons on the left as I have on the right, right? Remember, basic double check in organic chemistry, count carbons. All right? There is one thing missing from my product here, and what's that? That moved pi bond. And where does that pi bond going to move to? Between carbons 2 and 3. Doesn't matter which way we count here. Your pi bond will always move between carbons 2 and 3. So maybe let's just say, if we do this little numbering trick here, we can say our new pi bond between my green 2 and 3. All right, so again, we start out with what we know. We know we're going to form a six-membered ring. We know that 4 carbons from that six-membered ring are those conjugated pi bond carbons, 1, 2, 3, 4 for my conjugated pi bonds. The other 2 are about my pi bond in my dienophile. Those are the 6 that make up my ring. So we just number to keep track of who's who, and then we have to remember to include that pi bond between carbons 2 and 3. Okay, so now we're going to make it a little bit more difficult. Here, I kind of gave you the orientation that you would see in your product, right? So now I'm going to rotate these things about, make them a little bit more tricky. Okay, so try to do the same trick that we did above to predict our products of this Diels-Alder reaction. You got one extra pi bond. What are we going to start with drawing? That's six-membered ring. Start with our product. We know it's going to be a six-membered ring, and then we just got to figure out what six carbons make up that six-membered ring. Close. You're on the right track. You are missing, count your carbons. You're both missing 2 carbons. Yeah, you're missing 2 carbons as well. Oh, you are too. Count the carbons specifically in your diena file. I would look at how many carbons are in that diena file again. Yeah, you're missing 2 carbons. There you go. Yeah. Let's go. Cool. So same thing. Missing 2 carbons. Count your carbons in your diena file again specifically. It's almost there.
Details for a bag of chips.
Cool. Nice. Yep. Nice job, son. All right, so a lot of y'all are on the right track. A lot of you missing just 2 methyl groups. I'm going to draw my 6-membered ring. Okay. In my 6-membered ring, I know my 4 carbons from my conjugated diene got to be there. And my 2 carbons, specifically those about that pi bond in my diena file, got to be there. All right? So now I'm just going to number to keep track of things. Call this 1, 2, 3, and 4. And this one will be purple 1 and 2. Same thing over here. 1, 2, 3, and 4. Purple 1 and 2. All right, so as y'all had, we had this whole other cyclic structure here. Carbons 2 and 3, linking carbons 2 and 3 rather. And we have our pi bond that we know has moved between carbons 2 and 3. But if I count on my diena file here, there are 2 methyl groups on carbon 1 I need to include, and 2 methyl groups on carbon 2 I need to include. So yeah, you just short those 2, all right? So, and again, an easy double check, count the carbons, right? Same number of carbons on the left as we have on the right here. Cool. All right, we're going to sort of do this next time as well and kind of complicate things. There's 2 more kind of quick things that we're going to go over before we finish off for today. The one we're just going to simply label as alkynes can also be dienophiles. All right, so our very first example that we did, I'm going to take this and kind of get rid of all these ugly markings, was using an alkene. Try to simplify things a little bit. All right, now I'm going to play the same game. but I'm going to use an alkyne as my dienophile. So I'm just going to add one more pi bond over here. And I want y'all to try to tell me what the product would be if we used a triple alkyne, a triple bonded carbon instead of a double bonded. You're on the right track, not quite. Not quite benzene. Only one extra pi bond. There you go. It stays exactly where it was before.
Isolated.
Nice. All right, so we still form our six-membered ring. We got our two new sigma bonds. Our pi bond moves. So we still got that six-membered ring. Our pi bond has moved, but I'm missing one thing from my product side here. My alkyne had that additional pi bond here, and that didn't get touched at all in this reaction. So that's just still going to remain on my product side. All right, so I now have a pi bond, still have a pi bond, and I guess we can color our carbons the same way as we were doing before, just to be clear. Still have a pi bond between those two dienophile carbons. And so this product that we formed is also a diene. Is it conjugated, cumulated, or isolated? It would be isolated. We got these sp3 hybridized carbons effing up the communication between those two pi bonds. All right, and then lastly, what we're going to talk about is everybody's favorite topic, which is stereospecificity in a reaction. That's not how you spell it. Specificity. Is it a C? It doesn't matter. We're going to roll with that. Is it a C? Okay. It looked so wrong at first. I'll have to look that one up. Anyways, doesn't matter. Specificity. If you loved stereospecificity last semester, you're in luck. No, I'm kidding. It's actually the best case scenario. These Diels-Alder reactions preserve your dienophile stereochem. I think I could have gotten that one. Preserve, Jesus. I'm on it today. Okay. Preserves dienophile stereochem. So what do I mean by that? If we take, let's just take our simple diene, our 1,3-butadiene in its S-cis conformation. But now we're going to have a dienophile that has a specific stereochemistry. All right, we're going to form our six-membered ring. We had our pi bond move. All right, but what else do I have to include on those purple carbons? Those two methyl groups. Now, because I started out with a stereo-specific diene here, this would be a dienophile. This would be a trans dienophile. Those two methyl groups are pointed in opposite directions. That means that when this ring forms, I'm going to get a trans cyclohexene ring here, dimethyl cyclohexene. So those two methyl groups would be pointed on opposite sides. So my trans alkene leads to a trans cyclohexene. Let's just say a trans cyclic If instead I had started out with a cis alkene, what would my product be? Cis, right? So best case scenario here, we're just going to preserve the stereochemistry of our dienophile. Whatever the stereochemistry of our dienophile is, that's the stereochemistry of our ring, of our product. Cool. All right, and we'll pick up with these Diels-Alder reactions as well as introduce one more, our last one for this chapter, our electrophilic addition to dienes. What's up?